Okay, so now what I want to do is I want to do some practice first law problems. And so we have a first problem that is calculate the change of internal energy for a system undergoing an endothermic process in which 15.6 kilojoules of heat is absorbed and where 1.4 joules of work is done on the system on the surroundings. Okay, so we'll set this up on the light board. Okay, so remember the first law of thermodynamics is that the change of internal energy of the system is equal to any heat exchanged with the surroundings plus any work exchanged with the surroundings. Okay, so what we need to do is we want to try to figure out the change of an internal energy. So we have to figure out what Q is and what W is. And probably the most important part of this problem is that we assign the sign of the number correctly. So that's pretty important. So what's Q and what's W? Okay. We have looks like the internal energy of the system undergoing an endothermic process in which 15.6 kilojoules of heat is absorbed. Okay, so we have a system that is receiving energy or heat from the surroundings. And so the system is basically increasing in energy. So this is an endothermic process. And so if the system is receiving energy, if the energy is coming in from the outside, it's heat, then Q is going to be positive. So it should be positive 15.6 kilojoules for energy. Okay, how about work? And it says, and where 1.4 kilojoules of work is done by the system on the surroundings. Okay, if you have work done by the system on the surroundings, that is the case, then work is negative. So I'm going to put a negative here. And then I guess we have a value for that is 1.4 kilojoules. And so basically here you have delta U, as you're trying to find the change of the internal energy, is going to be equal to Q plus W, which is going to be equal to 15.6 kilojoules plus negative 1.4 kilojoules. And so the 15.6 kilojoules is the heat, and the work is the negative 1.4 kilojoules. And so the answer should be, as I've gotten on the screen here, which is 14.2 kilojoules. Okay, so let's move on. Okay, the next problem. A potato can be fired from a cylindrical tube in a demonstration called a potato cannon. A fuel is placed underneath the potato and ignited, and the potato is launched in the air. If the burning of the fuel performs 855 joules of work on the potato and produces 1,422 joules of heat, what is the delta U of the burning of the fuel? Okay, so I think what would probably help me when solving this problem is just kind of drawing a picture so I can sort of understand what the system is and what the surroundings are. So we have a cylindrical tube, and then we have a potato in it. So here's the potato. Okay. And then we have a fuel. The fuel is going to be underneath here. So I'll write fuel here. Okay, so what could be pretty important in helping me understanding how to assign correct signs to Q and W is understanding what is the system and what is the surroundings. And so I think what would be good to do is assume that the fuel here is the system. So this is the system. And the potato and everything else outside of the fuel is the surroundings. Okay. So what we want to do is we want to find the internal energy change for the burning of the fuel. So we want to find delta U, which is equal to any heat exchange with the surroundings plus any work exchange with the surroundings. Okay, so what we're trying to do is figure out when this fuel reacts, it's going to have an explosion, and we're going to have changes in the internal energy of the fuel. Basically, you're producing carbon dioxide and water, which have lower energy. So what may be happening is that this extra energy will maybe be released and maybe doing work. And so again, it looks like it's going to have some energy that is going to be heat that is being released onto the potato, and then you're going to have some work done on the potato. So Q here, it says, and the potato is launched in the air, if the burning of the fuel performs 855 joules of work on the potato and produces 1,422 joules of heat. Okay, so Q is, we have a fuel that is burning, and so it's releasing energy, it's releasing heat, it's exothermic. So Q should be 1,422 joules. And so it should be a positive, or excuse me, it should be a negative sign because it's exothermic, right? So it's a negative sign. And then work, so it looks like the fuel is doing work on the potato, which means the system is doing work on the surroundings. And so what that means is that the work term here should be negative. And so I guess we're given the value for that. So it's negative 855 joules. And so the change of internal energy is going to be equal to the heat plus the work. So it's going to be equal to negative 1,422 joules for the heat plus negative 855 joules for the work. And that should be equal to that answer there, which is negative 2277 joules should be the change of the internal energy for this problem. Okay, so we're going to move on to a new problem. Okay, see what we got next. Okay, so the first thing before we counter a couple of new problems, what I need to do is talk about something called pressure volume work. And so what pressure volume work is where you do work when you have a system that is undergoing changes of volume against a certain pressure. And so in the end, this kind of work with the changes of volume against the pressure is going to be measured in joules. And so when gases expand, then the delta V is going to be positive. But the system is doing work on the surroundings, so in the end, the W gas must be negative. So we have a problem here. So therefore, we need a sign change included in the equation below. So as long as external pressure is kept constant, the work is going to be equal to the negative sign of the external pressure times the volume change. And so let me talk a little bit about that on the glass screen. Okay. So I want to sort of explain why is it. I want to explain two things. So why is work in joules going to be equal to pressure times delta V? And the other thing I want to explain is why is there a sign change from pressure delta V into work? Okay. So the first question is, why is pressure times the change of volume going to be equal to work in joules? Okay, so here's one way to think about it. So work is going to be equal to negative pressure times the change in volume. And so one of the things you'll learn in 110 is that pressure is really the force of the molecules acting over a certain area. And so I'm just going to write area, and so it's going to be an area of space. And then you know what delta V is. That's going to be a change in volume. So I'm just going to write delta V here like that. Now let's just include what some units are going to be and see what happens. So we have, I'm just going to leave F as force. Okay, what is area? So what area is as you know, it's a distance times a distance. And so for example, you can measure a distance in meters. So we can think of it as meters times meters here. Now, what is volume? Volume, as you know, is a distance times a distance times a distance, which is going to be meters times meters times meters. And so what you can see is that 2 of the meters here in the denominator cancel out with 2 of the meters here in the numerator. And so we're left with a single meters here in the numerator. And so what you can sort of see now is that here, F times the single distance here is going to be equal to work, because that's how we originally defined work. Work, again, as we originally defined it, is going to be force times distance. And so we can sort of see how if you look at pressure times the change of volume, that's basically equivalent to force times distance. Now, the other thing that is odd is this. With these kinds of problems, you have to put a negative sign here when you take a P and multiply it by a delta V, and that will give you work. And so let's go ahead and explain why that is the case. Okay, so what is going on here is, let's say you have, well, let's draw this in a slightly different way. Okay, so let's say, again, we have a cylinder in a car, and let's say you have a piston here. I'm going to draw that here. And let's say you have a fuel here. Okay, and so we can sort of think of the fuel as the system and the piston as the surroundings. And so let's say it explodes. And so what's going to happen is the piston will be shoved down like this. And so it has blown up and it's pushing the piston down. So we kind of know right now that we must say at this point that because the system, the fuel, is doing work on the surroundings, we know in the end that we must have WB negative. That's basically what we had talked about previously. Let's take a look at what the simple math would end up being. And so, for example, what you can see is here we have an initial volume, say VI, and here we have a final volume. And so the change of volume is part of the process of the work being done. And so how would you calculate work here? So we would take the delta V, which is equal to the final volume minus the initial volume. And you can see that the final volume is going to be a larger number than the initial volume, right? So delta V is going to be positive. It will have to be a positive number. Now, P is just the pressure, and so it could be something like atmospheric pressure, so it's going to be P. So you can see, again, when you do the simple math for these problems, delta V, because it's a final volume by initial volume, will be positive. But in the end, the work term here, W, we know because the fuel, which is the system, is doing work on the surroundings, it must be negative. So what we have to do is put a negative sign into this equation, and then we can use it. Okay, so let's finish up here with a couple of problems. They're pretty simple. So calculate the work associated with the expansion of a gas from 46 liters to 64 liters at a constant pressure of 15 atmospheres. So what we're going to do is we have to calculate work here from a situation where we're given some kind of pressure and a change of volume. So the formula we use is W is equal to negative P change of volume, that. Okay, so let's go ahead and put in some terms here. So W is equal to negative P. So the pressure here is 15 atmospheres. And then the volume change is what? It's 64 minus 46 liters. And so let me go ahead and work that out. So it's 64 minus 46. So I get 18. So it's going to be equal to negative 15 atmospheres times the change of volume, which is 18 liters. And so you can multiply those two numbers together, and what you get is negative 270. And what are the units? The units are liters atmospheres. Now, one of the things you'll learn in physics is that when you have units of liters atmospheres, that is actually a unit of work. And so what we need now is sort of a conversion that takes work measured in joules and equates it to work measured in liter atmosphere. And so we have that in that problem. So you will note that there's 101.3 joules for every 1 liter atmosphere. And so if you want to convert a work number that is in liters atmospheres to joules, you must use this conversion here. So it's going to be times 101.3 joules over 1 liter atmosphere. And so the liters atmospheres would cancel. And so if you do that math, I think what you would end up getting is negative 27,000 joules, which is negative 27 kilojoules. Okay, so let's do the next problem. Next one's a little trickier. Okay. So a hot air balloon is being inflated to its full extent by heating air inside of it. in the final stages of the process, the volume of the balloon changes from 4 times 10 to the 6 liters to 4.5 times 10 to the 6 liters by the addition of 1.3 times 10 to the 6 joules of energy as heat. Assuming the balloon expands against a constant pressure of 1 atmosphere, calculate the delta U of the process. Okay, so again, what we have here is a situation where we're trying to find delta U, and you know it's going to be equal to Q plus W. Now, we're not given work per se. Instead, we're given a change of volume and a pressure. So what we're going to have to do is we're going to have to substitute into this work here that fact that work is equal to negative P delta V. So I'm just going to substitute that in here. So plus negative P delta V. Okay, so let's see if we can go ahead and assign variables. So what is Q? So it says, by the addition into the balloon of 1.3 times 10 to the 8 joules of energy as heat. So it sounds like that is energy that is going into the balloon as heat. And so that sounds like it's an endothermic process because the balloon is taking in the heat, it's getting the energy. And so Q here should be a positive sign. So I'm just going to indicate there's a positive there. And the amount of heat is 1.3 times 10 to the 8 joules. Okay, now we have to figure out P delta V. So let's see if we can sort of figure that out. So are we given kind of any information for this problem? So P, let's see what we have. P is going to be 1 atmosphere, so that isn't so bad. So 1 atmosphere. Now how about delta V? Okay, so we want, again, the final volume minus the initial volume. And so the final volume is 4.5 times 10 to the 6 atmospheres minus the initial volume, which is 4.0 times 10 to the 6 atmospheres. Let me add another 0 here to make the figures match. Okay, and so here the change in volume is equal to 0.50 times 10 to the 6, oops, not atmospheres, liters. There we go. Okay. All right. So delta V is that. Okay. So what we're going to do is just put in these numbers into the equation. So Q is 1.3 times 10 to the 8 joules. And then what we're going to do is we're going to work out P delta V. So it's going to be plus a negative P, which is 1 atmosphere. And delta V is 0.50 times 10 to the 6 liters. Now, one of the things you can sort of see right now, we have a bit of a problem in that here the first energy term is in joules, but this second energy term from work is not in joules. It is in liters atmospheres. And so one of the things you're going to have to do is you want to convert liters atmosphere into joules. And so you can actually do that within the problem. So I'm going to go ahead and do that. So it's going to be times 101.3 joules over 1 liter atmosphere. And so you can see that the atmospheres cancel and the liters cancel, and so we should be left with an answer in joules. And so let me go ahead and work this out. So it's equal to 1.3 times 10 to the 8 joules minus, let's see, it's going to be 1 times 0.5 exponent 6 times 101.3. And I get, let's see, divided by 1 exponent. And I get 5.065 times 10 to the 7. So I'm just going to subtract that from 1.3 exponent 8. And I get, let me do that again, 1.3 exponent 8 minus 5.065 exponent 7, and I get 7.93 times 10 to the 7 joules, which is the answer we wanted. Okay, so thank you for listening to that. We will see you next time.